David, welcome back to Talk Python to me.
Thank you so much for having me back, Michael. It's really an honor.
Yeah, it's an honor to be here with you. Got some really fun stuff to talk about. Computer science from scratch. What does that even mean? We're gonna find out because you wrote the book on it, and yeah, we're gonna dive in.
Yeah, I'm excited. And this book just came out, so it's kind of fresh off the press. And I want to thank you for being the technical reviewer on the book, actually.
Yeah, it was really fun. You reached out and asked me, and I don't normally do things like that, but I'm like, that'd be kind of fun. It would be a good experience, and I do think it was. It taught me some about creating books, and I guess that pays off as well.
And congratulations, by the way, on Talk Python in production coming out.
Yeah, thanks. I started that last December, and it came out, I think, the beginning of this month, maybe end of September, something like that, but pretty recently. So yeah, I really appreciate it. It's going really well.
We're in kind of the same phase because Computer Science from Scratch officially came out end of September also. So we're just in this kind of, 1 month out from these books coming out. And so it's both, I think it's an exciting time for both of us. And I've started reading Talk Python in production and I'm really loving it. So congrats on it.
Awesome. Thank you. And I really enjoyed your book. And I had to read it with a little more detail than just appreciate it, right? I had to like take notes and help you with some feedback. So that was a really cool experience. And thanks. It's been almost it's over 5 years. Let's put it that way. It's been over 5 years since you've been on the show. We talked about classic computer science programs in Python, I believe it was. And yeah, it was really a fun and popular episode, but let's do a quick refresher, a quick introduction for you to everyone who's new to the show in the last 5 years.
Okay, so my name is David Kopec. I'm a computer science professor at Albright College in Reading, Pennsylvania. Actually just moved over here from Champlain College, where I was for the past 9 years in a similar role. And I'm also the program director of computer science and information technology. We're launching 3 new majors, a little plug for Albright, a revamped computer science major, an artificial intelligence major, and cybersecurity. And so I'm managing the launch of those for fall 2026. My background is for the past decade, obviously, as a computer science educator. I've written 5 books on computer science and programming, the most successful of which was Classic Computer Science Problems in Python, which, of course, I was on the show 5 years ago about. And this book, Computer Science from Scratch, is kind of for a similar audience. Both books are for Python programmers, folks who are intermediate or advanced Python programmers, but maybe who want to fill in the kind of computer science topics that they don't know, maybe because they're self-educated, maybe they learned Python on their own, they didn't have a formal CS degree, or maybe they did have a formal CS degree, but now they're preparing for interviews or transitioning to a more CS in-depth role, and they want to refresh on some of these topics. So both books are for folks who know Python, but want to go deeper on CS.
Right.
Classic.
They're not, here's how you do a loop in Python, or here's what itertools is. It's true computer science topics, right?
Right. And I think somebody at that stage would be very frustrated by the books. They really are. And so
Yeah.
we have to put that preface in. They really are for intermediate or advanced Python programmers.
Yeah.
I'm trying to reach the same audience, but they're totally different books in terms of the type of topics they cover. So Classic Computer Science Problems in Python was more of a data structures and algorithms type of book, did some AI type topics as well, but very much on the algorithm side. Computer Science from Scratch is more, let's build up the layers of the software stack from the bottom up that Python kind of runs on top of, so you understand what's actually happening under the hood. So how does an interpreter work? What's the hardware software interface like? We get that with emulators. And then there is still some algorithmic stuff as well, different topics than in the prior book, but stuff like a little computer art stuff, a little bit of machine learning. So we try, it's still a survey book, it's still pretty broad, but it's
Hmm.
more about the layers of the software stack than Classic Computer Science Problems in Python was.
Yeah. Yeah. There's some pretty low level stuff. And it's interesting that you're doing in Python, I think a lot of times that would be taught in at least a pointer based language, like C, or you can even see it being taught in assembly, like you're talking to the machine, like literally.
Absolutely. And if you took these classes, like if you took an architecture class, which I'm going to be teaching next semester at Albright, it's going to be an assembly language, right? And if you took a compiler's course, it's usually in something like C, or today it might be in a Rust, a low-level language where you do have that direct access to memory. But I wanted to make the book accessible, and Python is the most accessible language in the world. It's the most popular language in the world, and it's the language that we're increasingly using in computer science education anyway. So it is actually a little unusual to cover some of these topics in Python, but it makes the topics accessible to a much wider audience.
Yeah. It definitely makes it accessible to a wider audience. Let's take a step back and talk about this role you have in this new college university you're at. So you said that you're revamping the CS program. You're adding AI and cybersecurity. That's a big shift. Do you want to just talk to people about, how that's changing, why you decided to change? I look at a lot of CS programs, and I don't know how connected they are to the real world. So I imagine some of these changes are to sort of realign it with, what's happened recently.
Absolutely, yeah. So I'm coming from a college, that Champlain College in Vermont, where I was at for 9 years, which was a professionally focused college. So it was a college where we were preparing students for their careers. I moved now to Albright, which is a liberal arts college. So it's a college that's more teaching people how to think, creating great citizens, and hopefully we prepare them for their careers very well too. But there's that liberal arts foundation underneath everything. So one of the challenges in developing these three new majors was, how do you fit them into a liberal arts curriculum? And how do you make them relevant to careers while still being true to the liberal arts? And so what I found the best way to do it is to still focus on how to help people think computationally. And so there's a firm foundation of computer science and mathematics throughout all three majors. So whether you're doing cybersecurity, artificial intelligence, or computer science, you're going to have a lot of classes in common with one another. And we also need to infuse some of the issues we see in the workforce today. Like all of them will have a computer ethics course that's incorporated. And all of them will have an internship course that's incorporated. So students are getting real world experience as they're going through these majors.
I think that's a great idea. It's really important to have done, software engineering hands-on with other companies, real products and real product managers, in addition to just knowing the algorithms and foundations.
Absolutely, couldn't agree more. And so we're trying to blend the two, and and that's been one of the exciting things. And you asked why I changed. I was excited about this opportunity to build these new majors from the ground up. We'll be one of the first teaching colleges, small teaching colleges, to offer an artificial intelligence major. It's just been in the last 5 years that we've seen colleges start to offer an undergraduate major in artificial intelligence. And it's mostly been big name brand colleges like CMU that are offering these first artificial intelligence bachelor's degrees. But we get to be at the forefront of, how do you fit that into a small liberal arts college and still make it career relevant and still have that firm liberal arts foundation.
Mm-hmm. Are you concerned about letting all these hackers in on your network if you're teaching a cybersecurity
Well,
focus?
I won't be teaching the cybersecurity courses. So I'm firmly just in the computer science education course, and we're hiring additional faculty in cybersecurity and in artificial intelligence. I'm more on the management side of those two programs. But, look, it's more relevant than ever. When you look at actually the number of students going to college for cybersecurity, it's been exploding over the last decade. I just talked about how artificial intelligence has just come about as a bachelor's degree. Cybersecurity was kind of there 15 years ago. So cybersecurity started out as, maybe you took a computer security course at the end of your computer science degree. Then it became a concentration you could do within some computer science degrees. And then in the 2010s, it broke out and became its own bachelor's degree. And so we're seeing the same thing right now with AI. It started out, when you did undergrad computer science, maybe in the 90s, or like me in the 00s, you might have one course, like an intro to AI course, that you have at the end of your bachelor's degree. And then it started to be something where you do a concentration. At Champlain, I developed a concentration in artificial intelligence. Now, just in the last 5 years, we're seeing it break out from being just a part of a CS degree to being its whole own, adjacent degree. So I think it's an exciting time for that. Of course, there's a hype cycle right now about AI. So a lot of colleges are jumping in, and I think some of them are doing it the right way. And, having that firm foundation in computer science and mathematics, so it's durable. And some of them are doing it in kind of a shallow way. We're trying to do it the right way.
Yeah, that sounds great. And obviously, cybersecurity is one of those things that's highly valuable. Nobody wants to be in the news
Right.
for that reason, right? So companies are certainly looking for people with those skills. let's talk one more thing about the university. Not the AI focus, but just AI. One of the things I think is of all the places that's getting the most scrambled, changed, under pressure, whatever you call it, from AI, I think it's education in general. And I'm not talking just college. I'm talking, I don't know, like third grade on. As soon as the kids can start using AI, they're like, this is like the calculator with a rocket booster on it. You know what I mean? Like this will solve the problems. And I think there's a really big challenge for you as universities to connect with students, keep academic integrity as well. But there's also a huge problem, I think, for the students to not let it undercut their education and end up going, well, all I know is to do ChatGPT.
You're absolutely right. I mean, it's a huge challenge in computer science education, and I don't think the computer science education community has yet completely figured it out. Basically, what it breaks down to is exactly what you said. Students are just using ChatGPT or GitHub Copilot to do their homework. And if you're in a first year or second year class, I've been mostly teaching upper level CS for the past like 6+ years, and I'm teaching an intro class for the first time in a long time this semester. And it's been eye-opening for me to see how many students are trying to just do every assignment with ChatGPT, and we still have to give them basic assignments. When you're first learning how to do
Yeah.
a for loop or what a function is or what an if statement is even, right? You got to
You
write some
can't
of those
say
big,
implement a database and get back to me next week. You got
right,
to start
right.
somewhere.
So we still have to teach these fundamentals, but we have this opponent to us in some sense of this ease of access to something that can just do all the work for you. And so I'm sure that, like you mentioned, mathematics educators had similar challenges in the 1970s, 1980s as
Yeah.
calculators became prominent. So what I've done, and I've been adjusting since ChatGPT came out in fall 2022, I've been constantly adjusting and reevaluating, but I have had to go back to the future a little bit. And people might find this a little anachronistic, but I've heard about it from other CS educators as well. Going back to doing some paper exams. I know that sounds crazy, and I know that sounds
Yeah.
like bizarre, but at some point you need to evaluate if students actually know how to write a for loop. Because, while some people think LLMs are going to replace software engineers in the next 2 years, you still need to understand what it's outputting. And I don't know about you, Michael, but I don't think they're completely replacing
Oh, no.
software engineers
No
in the
way.
next
No
couple
way.
of years.
And
And
that's coming. I don't know how many people maybe don't necessarily. I'm a huge fan of agentic coding and what it can do for productivity, and it's incredibly powerful. But it's one of those things that is, it needs someone to guide it who knows how to do that, and then it becomes a superpower. If you don't, you end up with like, how do we end up on React? I thought this was a Rust project. Like, what happened here?
yeah. And you need to understand when it makes mistakes. You need to know how to correct those mistakes. And
Hmm.
of course, you need to be understanding everything that it's outputting, so you're auditing it.
Yeah.
So we are having a real challenge, especially in those intro classes, of how do you kind of force students to not use these tools essentially, because you're not learning anything if the tool writes the for loop for you when you're first learning how to do a for loop.
Yeah.
And so you have to find ways to encourage it, to win hearts and minds. I think, of course, that's a big part of it, is convincing students and being dynamic and enthusiastic about how good it feels to really understand how this actually works. But then there
Yeah.
has to be enforcement too, and sometimes that feels a little anachronistic, being forceful about it or going back to doing tests on paper. But we,
Yeah.
we have to have ways of ensuring the knowledge is actually there.
I feel like this is not just a college student issue, but I think it's especially relevant in that part of your career, that the struggle is not in the way. The struggle is often part of what unlocks your thinking. It's part of what like cements the knowledge and makes you feel a true sense of accomplishment when you're like, I tried this and I couldn't get it to work, but 3 hours later I finally figured it out, and I now understand iterators
Yeah,
finally. You know what I mean? And it's just so easy to push the easy button and just say, chat, why?
yeah.
you know?
And that's what feels good about being a teacher, is being there for those aha moments with students. I had some moments like that last week, and they reminded me, like, this is why you're in this career. It's really something that can become addictive to students. Actually, when they start having those aha moments, they want
Yeah.
more of them, and it
Yeah.
spurs
That's how
on.
it, that's how you end up at like 3 a.m. really hungry. Wonder why you haven't gone to sleep, but still programming. You're like, this is
Right.
amazing. I can't stop.
Right. And it takes a certain mindset to be able to appreciate
Hmm.
those moments. And I'll just, this is like a sidebar, but one thing we're also seeing in computer science education is we see a lot of folks who go into it sometimes for the wrong reasons. Folks sometimes go into computer science just because they hear this is a great way to get a good job, and if that's your only motivation going into it, you're
Yeah.
probably not going to be successful in it. Um,
Yeah.
Unfortunately.
It's gonna be tough. Yeah. It's gonna be tough.
Yeah.
But a lot of people are there for the right reasons. So I think that that's good. I think it's
Absolutely.
good.
And I hope with a book like this, folks who came in from the other side, folks who came in, because they had that interest, but they didn't have the chance to either go to university, maybe they couldn't afford it, maybe they studied something else and they're later in their career.
Hmm.
This will hopefully give them a bunch of those aha moments, and about topics that are deeper than just, how to write a for loop.
Yeah. Absolutely. Well, good. I mean, I feel like there's probably some middle ground you might be able to accomplish if you're like, all right, we're going to give you a laptop, a testing laptop that has no internet. Like we've
Yeah.
gone in there and crushed the network card.
Yeah.
Here, take the test, and here's
Yeah.
your thumb drive to submit your work. A potential, potentially.
Yeah, and we do stuff like that. Like I just did a test on, an online test for my students, and I'm just monitoring to make sure nobody's using the tools. But there is something said still for paper exams. I'll tell you why. Sometimes, even today, on today's tools for giving exams, sometimes you want students to draw something, especially if it's a data structures and algorithms class. You might want them
Hmm.
to draw a tree, and it's just actually easier for them to do that on paper. So when people hear paper, they might be like, "Oh my goodness, what are you doing that for?" No, there's real reasons.
Yeah, of course.
But yeah, we have monitoring tools too.
Yeah, very good. All right, let's maybe take a couple of different examples or different chapters from the book and talk through them. The first one, the first main topic is the smallest possible programming language, right?
Yes, and
Tell
so
us about this.
yeah, the premise of the chapter is what's the minimum that we need to have a programming language? And there's a famous programming language. I'm actually not going to use the name of the language on the show, I think, just because it has the F word in it. And I didn't make up the
Oh,
name of the
that's right.
language. It was developed 30 years ago, but we'll just call it BF, okay?
Yeah.
And this
Brain
language,
F star.
yeah, sure, brain app star. This language, it only has 8 symbols in it. I mean, it literally only has 8 symbols in it. Yet, it's what we call Turing complete. And
Hmm.
I won't go into the full details of what it means for something to be Turing complete, but let me put it this way. A language that is Turing complete can theoretically solve any of the same algorithmic problems as any other language that's Turing complete. And every programming language that you use is Turing complete, whether it's Java, Python, C, whatever. Of course, they're all Turing complete. This language with only 8 symbols in it is also Turing complete. So while you could code something like quicksort in Python, you could also code it in BF with just 8 symbols. While you could code a JSON parser in Python, you could also code a JSON parser in BF. So by learning this really, really basic language and actually implementing it, so implementing an interpreter for it, something that can actually run programs written in it, you really get to understand just how little we need to solve computational problems. We don't need much. We need very minimum amount of computing machinery and very minimum amount of syntax to be able to solve most problems. Now, would you want to solve most problems in PF? Of course not. We just use it as an illustrative example to show
Hmm.
this is how simple a programming language can really be and still have all the same capabilities as a more advanced programming language. And you might wonder then, why do we have such much more advanced programming languages? Because they give us a lot more developer productivity. They have more abstractions that let us think as human beings instead
The
of thinking like
expressiveness.
machines.
Yeah.
The expressiveness, absolutely. And so that's great that we have all of that. But if you really want to understand essentially what the language is doing at the lowest levels, you only need these few bits.
So, what's the key message here? Obviously, you're not trying to get people to become BF experts, right? I mean,
Right.
maybe learn COBOL over BF these days still,
You
right?
work for
Because
the
you could
Social
at least,
Security Administration. Yeah.
yes, exactly. There's going to be
Yeah.
some high paying COBOL jobs out there. But this is more about like writing an actual interpreter, right? Very much like C Python itself in a sense,
Right.
conceptually, right?
Conceptually, I mean, much, much, much simpler. And actually, in the next chapter, we get to writing a basic interpreter, which is like just one step up from BF. And we can talk about that in a minute. But yeah, it's
Uh-huh.
about understanding how it works at a low level. Like, what's it actually doing? And it feels good to make something that can run programs. A lot of people, when they get into computer science, are actually excited about like making their own language. So by doing these first couple chapters of the book, you're actually on the path to that. I think after reading these first two chapters, you could go implement your own simple language, and really make that kind of dream that a lot of us have come true. So it's about understanding how it works at a low level. I have to say the book is not a practical book. It's not like Talk Python in Production, where you're going to learn, here's some useful tools and tips and
All right.
strategies
Install this
to,
thing and set up that config and then
to do
run it
something
this
right
way.
now.
Yeah. Yeah.
Right,
Yeah. Yeah.
computer science from scratch is not going to help you build your next app like that you're building.
Not
But it
directly.
is not directly, but it is going to help you understand a lot more about what's happening under the covers, which is ultimately going to make you think more broadly as a software developer and understand different strategies that you might be able to use. I'll give you an example with this interpreter stuff. You might be writing a program that needs to have some kind of configuration files, and you want to maybe be able to parse those configuration files. Well, part of writing an interpreter is writing a parser, something that understands the syntax of the programming languages and starts to get towards the semantics. And you might want to be able to write a parser later on for some very specific configuration type format that you've come up with for or maybe even just a file format for more of like an Office type program. And you're going to need some way of understanding the techniques of how to parse that. Learning how an interpreter works will help you write that program later on. So it's about learning computational techniques, learning problem solving techniques, more than it is about like something that's going to necessarily be, this is exactly how you do this for the next app you're going to build.
It's not something that you would just stumble across most of the time, I think, right? You'll stumble across, oh, here's a web framework. You'll stumble across, oh, here's an ML library or something, but you don't typically stumble across, and here's how you build a parser from scratch.
Right. And so, there has to be that curiosity there. So I will
Mm-hmm.
admit that, if you have no interest and you're not the type of person who wants to understand how things work, you won't like this book. And, that is some folks, and that's okay. There's folks who go into programming because they're only interested in what they can build, and they're not so interested in how things work. And if that's you, this is probably not the book for you. But if you're the
Yeah.
type of person who has that curiosity and you really want to understand how everything's actually working under the covers, then this is a great book.
Yeah, absolutely. And it's a simple enough thing that you can grasp the ideas pretty quickly with this BF language, right? It's not so complicated that a day later are still trying to make the thing parse.
Absolutely. I mean, what's crazy is to interpret BF, you only need about 30 lines of code, 30 lines of Python. And then you actually have something that can run any program written in this language.
And to be
So,
clear, you have like something .bf files that you can put
right.
the language into, and then you say Python, this module, that file, and it'll run it as if it were an interpreter for that thing, right?
Exactly. Yeah, you're literally implementing the whole programming language in like 30 lines of Python. And I think what's
Crazy.
great about this too is it takes away the feeling that everything is magic. That's another thing I love when people read also classic computer science problems in Python is, sometimes when you think about how these things work, like in that book, we cover the A star algorithm, which is something that Google Maps uses. When you think about Google Maps, like it feels like magic when you use it.
Yeah.
But actually there's really understandable logical algorithms that are underneath the surface. It's the same thing here. Python itself might feel like magic to a lot of folks. But by the time you get through these first couple chapters, especially through the basic interpreter chapter, you'll start to be on the road to think, oh, you know what? I bet I could dive into the C Python source code with enough additional training and really understand it. It gives you that confidence that
Right. We've already
this
got
is
the
not just
parser.
magic.
You just got to
Right.
look at the byte codes and
Yeah.
and look at it go. Yeah. That's
Yeah.
pretty
Not
neat.
to say there's not a lot more there, but it just gets you on that journey and makes you see it's not magic.
Right. Well, it's that 0 to 1 sort of gap that's the hardest to cross.
Yeah.
Yeah. Like the second language, second programming language you learn, or the third or the fourth, they only get easier to learn, not harder to learn. Whereas, maybe when you're first starting out and you're trying to get something to compile and it won't even run, you're like, oh my God, how am I going to do? I can't even learn this one. And there's all these things I'm going to have to know. And that's really kind of upside down.
Yeah, absolutely. And so, when we think about understanding how Python itself works, I think the second chapter of the book about BASIC gets us, a lot further along on that journey because here, this isn't just a made up, well, BF it's a language that's been around in computer science education for like 30 years, but it's not a real language that people actually used. In the
Right.
second
Very few
chapter,
people ever said that they were BF programmers at a dinner party, right?
absolutely. But plenty of people said they were basic programmers. And,
Yeah.
it was the first programming language of a lot of people who grew up in the 70s, 80s, or even the 90s. It was my first programming language. And there was a dialect of BASIC called Tiny Basic that came out in the late 1970s. It was actually one of the first free software projects. And it would run on machines that just had 2 or 4 kilobytes of RAM. So that's why it was called Tiny Basic. I mean, it truly was tiny. And so we re-implement a dialect of Tiny Basic in chapter 2. So this is re-implementing a real programming language that people actually used for real work in the late 1970s and up to the early 1980s. And it can run real programs from that period. So you could go download a program from the late 70s. We were missing like 1 or 2 features from the real language. But if you have not all programs use all those features, you could actually run it in this interpreter. So we go from the first language where it's really an esoteric, educational, weird language to the second chapter. This was a real thing.
Yeah, absolutely was. I'm just going to give a little shout out to Visual Basic.
Yeah.
I don't know did you ever do Visual Basic?
I did, and I did a version on the Mac called Real Basic. So this is really esoteric, but anyone who used Real Basic, late 90s, I'm in your camp.
There you go. I don't know if we even today still have something as kind of as approachable and productive as Visual Basic was. For people who haven't used it, you're like, there's just no way. There's no way that this basic. But you would just get a visual thing. You would drag it together to build your, here, I want to have, literally you would drag over, here's a web browser. Here's the address bar. Here's a go button. And then you would double click the go button and would create an event handler. And then you would go web browser dot go to text dot value or whatever. I mean, that was literally, you could do it in 5 minutes. You could like create something that is a functional web browser without much. It was incredible. And so, yeah, I just thinking back to a few things I built with it. It was amazing.
Michael, a lot of people agree with you. There's a lot of articles that I've seen on blogs and stuff where people reminisce about Visual Basic. And I agree. I mean, for desktop app development, it was incredibly productive. I mean, it's still, I think it still rivals some of the tools we have for building web apps today. When you think about how easy it was to lay out a user interface. And for designers, it was great too, because designers didn't need to know how to code and they could lay out the interface in the same way that it would really appear in the program, which is different from how designers work today, where they'll often do mock-ups and the developer will have to take the mock-up and turn it into code. And so you kind of lose something there with the designer being able to have the final product in front of them as they're changing around how things look. So there were elements of it that we're still missing today, I think.
Yeah, I think it really hasn't been matched. Windows Forms from .NET kind of approached that, but it was still itself was also a little bit more complicated. Just there was something special about that. And now, don't get me wrong, it's not like I'm saying we should just go back to it, because the software we build is way more advanced, does a lot of other things, but there's just that lower area is just kind of missing. And I want to sort of transition from that to something else. Really, we're looking at these two examples of the BF language interpreter and the BASIC interpreter. I hear that to really understand computer science, really to work on these things, it's not preferable. I have to do a language with pointers, malloc, free. I got to work at that level, or I just won't understand anything. In Python, we don't really have those concepts. And the irony, I think, is Python has more pointers than C++, because there's like no stack at all, not at all. Really, I mean, in the interpreter there is, but not in your writing. Everything, even like a number 1 is just a pointer. So Python's full of pointers, but not in the way that computer science thinks about it.
Yeah.
What are your thoughts about that sort of tension, right? On one hand, you have this really understandable language talking about these ideas, but you're like, but the computer is calling malloc on a page of memory, and that's what's happening, and they're not seeing it.
Okay. So let me talk about it from a pedagogy standpoint.
Yeah,
So at my last institution, Champlain College, we had a big debate over my 9 years there. Should we do our first three classes in Python or in C++? And when I came in, the first three classes were in C++, and we actually decided over the years to keep it there for exactly what you mentioned. We wanted to give students both that high level experience with object-oriented programming, but we also wanted them to have experience with pointers, with memory management, and understand how things work at a low level. But in that same period of time, many schools have moved to Python because of the other thing we talked about, which is accessibility. I think Python simply is an easier language to learn than C++. I don't think that most people who know both languages would really debate that. And so if we're trying to make those first ramp up classes where you're first learning CS as easy as possible, I think Python is the way to go if we want to encourage more people into the discipline. That
yeah,
doesn't mean there
I
shouldn't
agree.
be a C or C++ course later on, where folks, maybe when they take operating systems or even as part of an architecture class to see how the assembly language matches to a C program, that kind of thing. It doesn't mean there shouldn't be C or C++ in the curriculum or Rust or whatever. But if we're thinking about what's best for a student who's just coming into the field, I think we need to think about accessibility. But at the same time, my advice to all students is learn one language well before you learn any other language. So whether you're starting with Python or
Yeah.
you're starting with C++, spend, a year or two on it and become really decent at it before you go and learn another language. And that's the biggest mistake I see folks who are self-taught make. The biggest mistake I see folks who are self-taught make is constantly switch around from language to language.
Right, right. I
It's a
need to
little
know this.
easier.
Okay,
Yeah.
I got it. Now it's time to learn this. And they're trying to fill all these gaps, right?
Right, right. Because once you learn Python well, a lot of the stuff in C or C++ will make sense to you. The pointers might not, but a lot of the other stuff, like how does a function work? How does a loop work? What are variables? What's a global versus a local? All that kind of stuff. That's going to make sense to you, and that's going to be transferable skills once you've really learned it in any one language across any other language. And then pointers you can learn later on. You don't need to learn that at the beginning of your CS education. It's not, people make it sound like it's some totally mystical topic. If you are able to do calculus, which basically every CS degree requires calculus one, you
You're
can learn
good.
pointers.
You're
You'll
good.
be okay. You can learn pointers.
Yeah, exactly. Like double integrals and all that kind of stuff is way worse. I feel like you could also cycle, right? So you could start with Python for a couple of classes, then go deeper, closer to the machine with C. But then you could come back and say, let's look at Python again with new eyes and try to understand interpreted dynamic languages better. Because now, you can take the red pill
Right.
and you can see the arenas and the blocks of the memory allocator and the GC and all that kind of stuff, right? I think you could go, actually, you didn't know any of this stuff. Nobody probably even thought to think, is this here? And yet look at what's underneath that you're building on top of, right?
Yeah, and also remember how long an academic semester is. It's 15 weeks. So if you're taking
Yeah.
a class in college, you're forced to be doing that same language for 15 weeks. That's really the challenge for self-taught folks is they could just spend 2 days on one, 2 days on another, right? But absolutely, you're right. Once you've had enough time in one, you can cycle to the others back and forth.
Yeah, fun. I personally am a fan of it being in Python because I feel like one of the biggest challenges to keeping people in computer science and programming is that they don't get enough early wins and early, like, yes, aha, right? It's like, okay, in week 12, we'll let you write a program, but we're going to talk pointers for a while. And then you'll finally get to make some, you know what I mean? Like, it's just so
Yeah,
delayed. And that's fine for certain people. But there's a lot of people who are like, oh, forget this. This
absolutely.
is not what I thought. I'm out.
And a huge part of that is the Python library ecosystem. How easy it is to drop Pygame into an intro class and get somebody building a really simple game. It's much harder in C or C++ to start integrating libraries and start having students understand how to use those libraries. And it usually requires a lot more knowledge build up to be able to
Yeah,
use
exactly.
pointers and stuff with those libraries. So Python just makes everything more accessible.
Awesome. Cool. All right. The next area that was pretty interesting and a little bit, maybe a little artsy,
Yeah.
is the computational art. Tell us about that.
Yeah, so there's two chapters in the book on computational art. The first one is really starting to understand what a pixel is on the screen. And the way we do that is we take modern photos and then we want to display them on like an ancient Mac, a Mac from the 1980s, like the
Hmm.
Mac Plus. And so we're going to take that modern photo and use what's called a dithering algorithm to break it down into patterns of black and white pixels, because those early Macs were only black and white. That will then still kind of look like the photo in black and white with these specialized patterns. So you're learning a bunch of things by doing this. One thing you're learning is learning really what is a pixel, and a pixel is really pretty simple at its base. I mean, it's just a color and a location. And so understanding how those pixels are organized, and really they're just organized usually as an array, or as a list in Python or a NumPy array or whatever. And then we're understanding some algorithmic stuff. So understanding that dithering algorithm is giving us some algorithmic practice. And then a cool thing we do at the end is we actually convert it into a file format called Mac Paint for displaying on, an ancient Mac. And that Mac Paint format uses a very simple compression scheme called run length encoding. So we're getting some other kind of algorithmic practice in there as well, understanding a simple compression algorithm. And we're understanding something about file formats too, which is really, kind of interesting CS topic as well,
Yeah, it sure
because we
is.
have to
Yeah.
properly format the file so the Mac Paint program on the ancient Mac will open it correctly. So,
Yeah, that was something actually when I first got into programming. I feel like I just stuck with text oriented files pretty much as long as I could because, looking at a binary file, like, okay, it has a header and we read the first few bytes and then the value of that byte tells you how long the rest of the header is and then like what this means. And then you skip. And I don't know, that was just, it was a bridge too far for me in my early programming days. And I was just like, wow, this is intense. And I was in awe. People were like, yeah, we just read the header and we do this. I'm like, okay, if you say so.
well, it's a classic CS trade-off between time and space. Anything that we do in a binary file, we could do in a text file. But binary files can be more efficient because they can be more compact and they can be faster to read from, for certain kinds of data. So, it's not that we have to use binary files, but understanding what a binary file format is like can be eye-opening to some readers. And
Uh-huh.
if you think about like modern file formats, of course, text formats are much more explainable, right? That's why we have the rise of things like XML in the late 90s up to today, or even JSON as a data interchange format. There's alternatives to JSON, of course, that are much more efficient for coding your web app in and for distributing the data back and forth. But
Right.
JSON
Message
is human
pack or
readable.
whatever, that
Yeah,
sort of
yeah,
thing.
yeah,
Yeah.
yeah. But JSON is human readable, so we can right away understand what it's supposed to represent and debug it really well. And so that it's one of those classic trade-offs. We can have something more efficient, or we can have something that might take up a little bit more time, but actually, is better for us as human beings.
Yeah. It's just, I think it's a good skill. And also something that was prevalent throughout the book is juggling bits and bytes, not just juggling bytes, but bits and bit flipping and shifting. And there's a lot of that going on, especially in the emulator layers and stuff like that.
Yeah, and even in the Mac Paint chapter, because the way Mac Paint stores pixels is as individual bits. So you have like a 1 or a 0 representing a black or a white pixel on the screen. And so you have to find a way to take those bits and compact them into bytes and then run the right run length encoding algorithm to compress it. Yeah. But there's a lot of that. And when you do really low level work in computing, you need to understand bits and bytes.
Yeah,
If
you
you're
do.
gonna work on device drivers or operating systems or file formats, you really need to understand this stuff at an intimate level. So we try to make fun, projects in the book that you get something, that's interesting as a way of making this, a little of sugar to help the medicine go down kind of thing. And I
Yeah.
also, we were talking about the computer graphics chapters. I also wanted to mention chapter 4 because I love the program in that called Impressionist. It makes images that look like an impressionist painter painted a photograph. So you give it
Hmm.
a photograph and then it builds kind of abstract art out of that photograph. And people usually think you need a neural network for that, or you need some kind of really advanced machine learning algorithm for that. But actually, we show in the chapter that you can do it using a pretty simple algorithm. All the algorithm does is it puts a vector shape on the screen, and it tries to position the vector shape so that it overlaps a region of color on the original photo that is close to the color in the vector shape. And if you keep doing that and you put enough vector shapes on the screen, you start to have like abstract shapes that look like the original photo. And so I think that chapter is kind of powerful because it shows you how a simple technique, a simple computational technique, can really have some pretty powerful output.
Yeah, it's a really interesting idea, and it comes out looking great. It's sort of it's approaching the problem from a different perspective, which I suspect is probably a pretty interesting CS lesson. There's these problems that are incredibly expensive and difficult to compute the one true answer, but then there's amazingly fast ways to get that's pretty much it answer. I'm thinking like Monte Carlo simulations and stuff like that. You're like, this could take 2 weeks or 3 milliseconds. Which would you prefer? You're pretty much going to get the same answer.
Yeah. And that's we talked about like why is the book in Python, and that is one of the challenges of writing the book in Python is simply Python doesn't have great performance when you write in pure Python. And so we've all seen the benchmarks where Python's like 50 or 70 times slower than C on certain benchmarks, right? And yeah, honestly, for some of the programs in this book, you really see that performance deficit you have with Python, like the abstract art chapter, where if I wrote that same program in C using some C graphics library instead of in Python with Pillow, even though Pillow I think is mostly implemented in C anyway, but still just with the overhead of having our algorithmic part of it in Python, that program is probably 30, 50 times slower than it would be in C. So you have to wait like 20 minutes to see that abstract art that would have been like less than a minute in a C program.
Not that it's relevant to the book or the courses, but you probably could bring in some optimizations like Cython or is it Numba? A couple of the things that'll take just the inner two loops and just make them go different, but it's not the point of the book.
That's true. And so I put that as an exercise for the reader in the NES emulator chapter, because the NES emulator chapter where we actually build up a real NES emulator. So this, I didn't write in the book for legal reasons, but it can actually play Donkey Kong. So it can play Donkey Kong from the original Nintendo
Incredible.
Entertainment
All right.
System.
Let's talk about the NES, the Nintendo Entertainment System.
Yeah. So, I mean, the NES, a lot of us remember growing up with, and if you're of a younger generation, this was like the main video game system of the 1980s to early 1990s that everyone had. It's where the original Super Mario came out, the original Legend of Zelda. And, it's actually, of course, like all video game systems, it's a computer. And being a video game system from the 1980s, it's a pretty simple computer, actually. Yeah. It has a 6502 microprocessor, which is the same microprocessor that was in the Apple II or the Commodore 64 or the I think the TRS-80 also. And that microprocessor, it only has 56 instructions, the NES version of it. And so you can write an interpreter for that microprocessor pretty compactly, not quite as compact as the BF interpreter in chapter 1, but compactly enough that it's only a few hundred lines of Python to be able to really write a simulator of that CPU. And so the NES is just that CPU plus a graphics processor called the picture processing unit, plus an audio processor. So in the chapter, we implement the full CPU. We implement a simplified version of the PPU, not advanced enough to run Super Mario Brothers, but it is advanced enough to run Donkey Kong.
Nice.
And we don't implement the APU. So the audio processing unit's a little more complicated, and we don't do the audio. But we do all of this in the chapter, so you can run real NES games. And what you're getting to understand that software-hardware interface. You're starting to understand how does our software actually get run on hardware by re-implementing what a CPU actually does. And you're re-implementing the memory map too. So how does the CPU connect to memory? How does the CPU connect to the graphics processor? You're doing all of that in that chapter. And so it's kind of
before you talked about writing an interpreter for the BF and basic languages, here you're completely emulating the hardware of the NES, and you're giving it the potentially given it open source NES games and it can run them, right?
Correct. Yeah, it runs several NES open source games. Like I said, I didn't put it for legal reasons, but it can run real commercial games as well for the NES. And so you're doing the whole soup to nuts, like entire system except the audio. But it is Python and it's pure Python, except for, of course, the library we're using. And we're using Pygame for displaying the window, which is written a lot of it in C. But because it's pure Python, the emulator doesn't run at full speed. So it runs on my Mac, it runs at about 15 frames per second. The real NES ran at 60 frames per second. So we leave as an exercise to the reader, yeah, go use Python or something like that. And I'm sure you can get this up with several different techniques, not just with, you can definitely with Python, but with several different techniques, you could get this up to 60 frames per second, but you're going to have to incorporate something that is, using that gets outside of just pure Python.
Sure. There's a bunch of ways that you already mentioned, but one new way that's kind of officially new just this month is free threaded Python. And I went back to my async programming course where there's a lot of examples of like, let's do this synchronously. Now let's do it with threads. Let's do it with multiprocessing. Now let's do it with async IO, right? And see like how those all compare. And the threads one, anything was computational. It's like, yeah, it's the same speed or maybe even slower, right? But then I did UV run -- Python 3.14t and it went 10 times faster or 8 times faster on my 10 core machine. And it's literally just running on I didn't change the codes from free threaded Python and it just took off. So I'm thinking here, there's graphics amongst many things is primed for this like embarrassingly parallel processing.
Yeah.
You could break up the screen into like little chunks and go, well, we got 10 chunks and 10 cores. Yeah. Let's go at it. What do you think about it as a plausibility?
Unfortunately, for a lot of emulators, especially emulators that are for more modern systems, threading would be a huge advantage. For the NES, it's not because of the way that everything was timed. So every time that the CPU does one cycle, the PPU, the picture processing unit, has to be timed to do exactly 3 cycles. So you can't just go ahead and you don't just give it work. It's not like a modern GPU where you just give it a bunch of chunks of work. It works on its own and then provides that to the screen. It's completely synchronized to the CPU. And so is the audio processing unit too. So it all has to kind of be synchronized within a single thread.
And all the games assume that that's how it works, right? That's how they have it all set. Yeah.
Yeah. And what they had what was called a V blank period, which was a period where it had already drawn the screen, and then it actually tells the CPU, hey, I'm done drawing the screen. Now you can do all kinds of work and be ready for the next time that you draw the next frame again. So they had really tight synchronization between the graphics and the CPU.
Interesting. Still cool. Still pretty cool. There's a lot going on there. If you want to understand hardware, that's a pretty low level look at it, right?
I think it's kind of the crown jewel of the book. There's a lot of people who are interested in emulators. And what I found before writing the book is there's not a single book out there that talks about writing an NES emulator, which is the most common emulator that people want to write. So I think this is the first book that has a chapter on writing an NES emulator. I will admit I was a little scared of like if Nintendo's legal team is going to like be upset about the book or something like that. But we did research on it. I mean, everything we're doing is perfectly legal in the book, in the United States at least. So, but
scary,
anyway,
right? Yeah, but yeah, absolutely.
And we put a big disclaimer at the top of the chapter, as you remember reading. But
I have a Nintendo story for you.
Great.
From when I was young. And I think this is very, very late 80s, early 90s, last century. Now, this was not me. Someone I knew, someone I was friends with, had, I think it was a Super NES. Okay. And people may not remember, but they had these big honking cartridges go chunk, and you would chunk them down in there. You would you would basically reboot the NES and it would boot up from the big game cartridge you put in there. And there was this guy that they found somehow, because there's no internet, maybe through a BBS. I don't know how this was found, But they found this guy who built a thing that the bottom half of it looked like a game cartridge. The top was this whole computer that at the top of it, it had a 3.5-inch floppy drive.
Wow.
So you would go to your BBS, you would find a game, you would put it on the floppy, and then you would slot this huge extra computer down into the NES, and you would turn it on, and it would like delegate the file IO through the little fake cartridge back to it, and it worked like crazy. It was perfect. That guy was not in business for very long. The guy who sold them, not my friend, but the person he got it from wasn't available after a while.
So Super NES comes out in like 91. So
It
this
might have
is
been a
like,
regular. No, I think I might have been in college. So yeah, it would be 91 onward. Yeah.
okay. I mean,
1993.
that is very advanced, like for that time. When you think about the type of stuff people like were modding at that time, that guy was a genius. Like,
Yeah, he was. He should have been hired if he
Right.
wasn't. You know what I mean?
yeah, absolutely.
Yeah, he was building them himself out of his dorm room or something. I don't know. I think it was in Manhattan in Kansas State University. I'm not sure where the guy was, but
Wow.
oh well. Anyway, yeah, that guy was playing with fire.
Yeah, absolutely. And you know what? Sometimes like understanding how the ROM cartridge works, right? Like we think again that it's like all magic, right? But actually what those big cartridges that we had that we like inserted in the NES were is they were mostly plastic, like that did nothing. And there was a little ROM chip like inside the big hunk of plastic. And the ROM just stands for read-only memory. So most of them were just like a big chunk of memory with a very tiny bit of logic chips that were called mappers on the NES that said like read this memory at this time. But again, it wasn't really magic, and those cartridges looked so intimidating, but they were really just a big piece of memory.
Yeah. Think about how much you've got to make that work right before you ship it.
Yeah.
There's no patches. There's no download and update. Once it's shipped, and it's burned into the ROM, and that's it.
I have some friends who work in game development, and like before they even ship the 1.0, nowadays they're working on the first patch. Like, and they just know they're not going to ship like the perfect program in 1.0. Now, to be fair, games were much simpler in the 1980s, right, than they are today. But they had to be perfect, like literally had to be perfect. And so there was a certain, I think, different attitude around game development then than there is today. And remember, they were also working in assembly language. So, you know,
Not even an easy language to work in.
I don't know if people like this word, but I would call it kind of hardcore writing NES games in the 1980s.
It was, that kind of programming. It was just different. It was just different. Like you had to be so detail oriented, and you had to be so thorough. It's almost like writing, spaceship control software type of thing. Not quite, but almost.
And the machines were so slow. The NES, which we emulate in Chapter 6, ran on a 1.8 megahertz CPU, 6502. 1.8 megahertz, right? So Super Mario was like an incredible accomplishment on a 1.8 megahertz. So people had to worry about all these computer science topics in a way that they don't today as programmers, because you had to squeeze every last bit of algorithmic performance out of the machine. And so today, I think we have sloppier software today because we have an embarrassment of riches. We got such powerful computers with so much memory that people don't worry about writing things as efficiently as possible. And so we end up with, inefficient software sometimes because people don't bother to do the algorithms right.
Yes, but I'm going to put a little double dagger, like see the footnote by your comment. Absolutely true for software. Not necessarily true for software developers.
Agreed.
Right? The efficiency of writing a 99.9% correct Python program, how quickly that gets done versus like something in assembly language straight on a ROM.
Yep.
You know what I mean? These are I think this is an interesting arc, and maybe you could speak to it a little bit from your academic perspective, but I think it's a really interesting arc of, it used to be really hard to program, and we'd solve small problems with lots of effort. And it's getting easier, and a lot of times it gets easier. People say, well, there it goes. Job's over. There's not going to be programmers anymore because everyone can do it. And we just solve bigger, more complex problems. And it just keeps building, like a web app, a basic e-commerce app from today was a keynote presentation of how like a Fortune 500 company pulled it off in 1990. You know what I mean? Like, here's how we got the SSL termination special machines to handle the SSL decryption so that we could do this under 2 seconds a request. You know what I mean? Like crazy stuff.
Yeah.
What do you think about this?
Well, it's not an either or. I mean, we want developers to be productive and we also want efficient software. So, I mean, the good news is that means that after we make it easier and easier to build software, we still need folks who are going to work on optimizing that software after it's built. So there's still jobs for software developers who are interested in that. I think you actually touch on this in Talk Python in Production to some degree, because you talk about in the book the appropriate level of complexity for the type of app that you're building. And so you talk about like, maybe you don't need a Kubernetes cluster if you're just building, something for 10 million requests a month and not something for a billion requests a month.
Yeah, and it's going to be run by one person or one person part-time versus a team or somebody who's a DevOps expert, right?
Right. So if I'm working on, a run-of-the-mill e-commerce thing, maybe I don't worry about squeezing out every last bit of performance because I want to productively make something that, like you said, is 99.9% of the way there as quickly as possible. But if I'm building a 3D game, they still build most 3D games in C++ because they need to squeeze out every last bit of performance, even if it's a little less efficient for the programmers. The programmers could write the games faster, maybe in another language or another framework than they're using, whatever, but they use something that squeezes out every last bit of performance. So I think you have to think about what is the app that we're building, what is the domain that we're in, and it's just not an either or. Like, we want to have software that's both developer productive to build, but also that's efficient to run. And it's an ongoing process. We might need to make that trade-off more in the way when we're first building it in developer productivity. And then as we're maintaining it, maybe we go more towards the efficiency side. But if you don't think about some of the efficiency things up front, you can end up in a bad spot because you could get some technical debt. You could end up in a situation where it's hard to undo some of the algorithmic mistakes that you made early on and the system starts to depend on. So you should think about it at least a little bit.
Yeah, absolutely. And I think, you're talking about they've got to squeeze out that little extra bit of performance because they want high frame rates. They might have to squeeze out that little bit extra performance because it's either possible or not possible. You look at some of the stuff in the Unreal Engine these days and you're like, that's real time. That's the game. That looks like a rendered CGI movie, not a game.
Yeah. And I mean, so a lot of it is being done for us today by library authors, right? So library authors are thinking about a lot of the low level stuff. So us as like run of the mill developers don't need to, which is great. But if you're doing something really de novo, something, with an innovative algorithm, you still need to consider efficiency at least. Right?
Yeah. And the other thing is you can write really slow code in C, and you can write really fast code in Python, or vice versa. It's easier to make it slow in Python, to be fair. But algorithms and data structures are tremendous influences, right? If you should have been using a set or a dictionary, and you're using a list. Yeah, you're probably having a real bad time performance-wise.
And you caught me multiple times on the technical review in places where I should have used a set and I used a list. So thank you for that.
Yeah, you're welcome.
But that's a great example. I mean, just knowing that basic fact that, in this situation, just swapping out, which is a simple switch, by the way, one data structure for another can totally change the performance characteristics. That's the type of things you do learn in the CS degree that you don't necessarily learn when you're a self-taught programmer kind of hacking everything out on your own, which is why a book like Classic Computer Science Problems in Python or maybe Computer Science from Scratch is good for that.
Yeah, it exposes you to this. Here's a data structure you haven't thought about, but here's why we're using it and the advantages and stuff.
Yeah, absolutely.
All right, well, we've covered a lot. We've covered pretty much solved computer science in 2025. That's good. And then the book is bringing computer science to so many people who are self-taught. Like me, I went to college, but I studied many, many years of math and found my way into programming. So I took a few CS programs, but not so many. So, it certainly showed me many things that I hadn't seen. Like I've never emulated hardware before. For example, that was wild.
And Michael, I was reading in Talk Python in Production that you actually worked on Windows desktop apps. Is that
I
right?
did.
For
Yeah,
um,
for like 10 years, more than 10 years. I'm almost 15 years. Yeah.
wow. So I'm curious. How did you feel about that experience versus the kind of Python GUI frameworks that exist today?
Oh, you heard my rant about Visual Basic, and I
Yeah,
was
and
such
I
a
was
fan
thinking
of
of
Windows
that.
Forms. I started actually in C++, starting the hard way, doing MFC. I don't know if you ever played with
Yeah,
that or heard of that,
Microsoft
but
Foundation classes.
yeah,
Yeah.
yeah, and that was actually pretty decent for a C++ framework. And then as soon as I found Visual Basic and C Sharp, I'm like, this is so much better. It goes from weeks to days of UI work, and stuff like that. And it took me a while to really appreciate building for the web. I think I probably made that switch around the year 2000, just a little bit after that. But I really like the web these days. I think the web is special. I just wish it was easier to take apps from the web and get them to people. For example, Firefox canceled progressive web apps. iOS has them, but they're kind of, let's not talk about those. And if you know the secret, you can probably install one, but you probably shouldn't. And we're going to, like, if it's like right on the verge of one more step, and the web would be really a really good replacement for those. And now we have things like Electron and so on, which I'm not a huge fan of, but it's it's kind of what we need to make that happen. But we don't necessarily need Electron, right? It would be really great. I'm also really excited. I don't know how you feel about it, but I'm really excited about PyScript and the
Okay.
possibility of running Python for your front end stuff.
Well, I guess what I was getting at is why do you think Python has not taken off more for desktop GUI development? So like we've seen things
Yeah,
like
yeah, sure.
Kivy, of course we have PyQt and and several other frameworks that wrap into older C++ GUI frameworks. But like it's Python now is so mature, it's the most popular language in the world and
There's
still
nothing
one of these.
preventing it. Yeah, there's nothing
Yeah.
preventing it from making a really nice platform for desktop for native app development, right? Fundamentally, you could come up with a framework that abstracts talking to Objective C, the APIs there, or the Win32 API. One of the things I'm starting to realize that makes desktop development really different from back in the day, if you will, is there are so many gatekeepers and barriers to getting your app onto a machine, right? Like
Yeah.
if I built a cool desktop app and I gave it to you, your Mac would go, no, we're not running that. We moved it to the trash for you because it wasn't notarized,
Right.
right? And something similar happens on Windows. And so there's these steps you got to jump through. And I think there's just been too many gotchas and steps for anybody to push a framework or a way of doing this all the way through, right? I mean, in a sense, the web is kind of like good enough that we don't have to figure out a way to build this. I think honestly, if I were to be more concerned, I'd be more concerned that we can't create truly straightforward mobile apps with Python than desktop
Yeah.
apps. Yeah, what do you
Yeah,
think?
that's where I was gonna go to next. Yeah, and I mean, Kivy has been an attempt at that, but I don't really think it's gotten a ton of track from what I see. It doesn't
Yeah.
look like it's gotten a ton of traction in the way people in the Python community hoped it would. So
Yeah,
I don't have a
Beaver's
good
doing good work, but it's also not there yet, I don't think.
I wonder if some of the performance issues, are part of this. People expect one of the reasons we like desktop apps and native mobile apps over web apps is because we get instantaneous feedback and, really high performance in our user interfaces. And, I still find even a PyQt app sometimes a little bit slower than, a regular Qt app.
Yeah. Yeah.
It's unfortunate. For me, like the big want for the whole Python ecosystem is what started to be the focus, I think, of the core developers, which is performance improvements. Like,
Yeah.
I think that performance improvements would make everyone's lives in the ecosystem so much better, and so I think rightly that this has become like one of the central focuses of the core developers.
Yeah. Guido, Mark Shannon, Brant Bucher, a bunch of people whose names I'm not including. They've all done really good work over the last 3 or 4 years. I was a little bit sad to see Microsoft cancel that project or cancel the funding for that project. I mean, the project continues, but still,
I
like
even
what has happened is so much better that is really a big deal.
Yeah, and I even saw it in the course of writing the book. I started writing the book in 2021, and that NES emulator on the same machine was something like 12 frames per second in 2021, and by 2025 it was like 17 frames or 15 or 17 frames per
Yeah,
second.
nice.
So I saw it really, I really saw it in these computationally intensive programs in the book.
I'm pretty positive for it. I mean, there's a lot of things that could be better, but I think one of the real superpowers is it's approachable, but its ceiling of Python, that is, its ceiling of what you can accomplish is not that low, right? You can go pretty far if you have CS skills and ideas, and then, pip install, UV install, like the options of what is out there to just build and click together are incredible.
What do you think about, and I know you talked about it on the show before, I heard about a while ago on the show about Mojo and about
Okay.
a total attempt that, let's just redo it, and we'll get
Let's keep
speed by,
the language syntax, but not the runtime.
right. And I mean, PyPy is also, of course, kind of an attempt at that as well. But, and some people call for it, right? I see sometimes people are like, why don't they replace CPython with PyPy? What do you think about kind of just like the whole,
Gosh.
maybe it's too big a topic for the end of the
No,
episode.
it's interesting. I think all of those are interesting. I think the Mojo performance story is very powerful. It's also really hard to bring over to CPython because there's so many different ways that it's used, and there's so many, it runs on this piece of hardware doing this thing that we just could never optimize for. So, and then, like I said, with 600,000 or whatever there are packages, how much of that are you willing to carve away to get
Yeah.
a faster language? And what I think also is a really interesting aspect that people might not think about or take into account that often is you'll see a lot of these benchmarks like here's the solving the three body problem in Python, and here's solving it in Mojo, or here's solving the three body problem in Rust. And look at that huge difference. But what often happens in Python is you find yourself orchestrating native code anyway. Like, okay, we're going to use polars, and we're going to do this thing. Like, but when I call the polars functions, I'm no longer running Python. I'm running like a drop of Python and a bunch of Rust. And
Yeah.
then you write back in the same, or I'm talking to a database layer, or I'm talking, there's like or my
Yeah.
web app is running on a Rust-based server. Like, there's just all these little parts where a lot of times your code speed is more about how you're putting the pieces together.
Yeah.
Not always. If you're doing computational stuff, that's out the window potentially. But when you're kind of, you're doing machine learning, you're doing web apps, you're doing database calls, a lot of these are like just a layer and then off it goes.
Yeah, that totally makes sense. But then I think it is holding Python back from some of those, some of these real interesting domains that people want to get into, especially when they're first learning programming, like 3D games, like, I don't. Let's stick with that because I'm thinking ones for
Yeah.
people in computer science education, like a lot of people who study computer science is because they want to make a game, right?
Sure.
And when they want to
And
make a game,
I can see a world, like look at one of the biggest game companies in the world. It's Unity,
yeah,
right? Right. As a foundational, like building your game with, not creator of games. They're built, I believe, in C# and .NET, if I remember correctly.
yep,
And that's a faster language, but it's not raging fast. It's a lot faster, but it's still a decent way from a C, like a pure C language, right?
yeah,
A pure C implementation. And they're really, really successful. They got close enough. I could easily see some company go, we're going to build a game engine and we're going to use Python as the language to get as many people who have been left out in the cold, in a sense, to do it. But we're going to do a Mojo-like thing, or we're going to do something where you don't get to use every library, but do you really need Flask in your game? Not in your game. You know what I mean?
yeah.
We're going to build like a a smaller, focused, high performance version that looks as close as it could be. And we're going to sell you a game engine and a way to ship those games on Steam, a way to ship those games on Metal to Mac OS, et cetera. Right? Like I could see that world happen.
Yeah, yeah.
I don't
No,
see me making that world, but I could see that happen. And then actually, I think it would be okay. How do you feel? Like, do you see that as possible?
no, that makes total sense. I think another thing we think about is like how much are skills becoming more transferable because of LLMs. So can somebody who already learned Python well now quickly pick up C Sharp in Unity because the LLM is doing a lot of the detailed syntax for them, and they just have to understand the programmatic ideas. So is like, maybe Python will continue to always be this great first language for everybody, and it'll be easier for people to now transition to other languages for specific domains. And so it matters
Yeah.
less that we have everything in the original language.
Okay. Out in the chat, there's the recommendation for that's Godot. Are you familiar with Godot? I'm not super familiar with it.
I think it's an open source game engine.
Yes, that
and
much I know, but that's
I
where my knowledge stops.
right, and I think it has like it's like a Godot script or something, or G script or something is its language, which I think has more of a Python like syntax. Somebody in the
I
chat
see.
can correct me.
Yeah.
Um,
Interesting. Okay, but I think if you took an end-to-end thing, it's not just a matter of like, oh, you can run the game engine with this. You've got to take it all the way to here's how you ship your games. Because soon, what is the very first thing you want to do once you get your game working and fun? You want to show your friends. You know what I mean? And you've got to
right.
find a way to send it out.
So this goes back to what you were talking about earlier, is all the hurdles around, getting something on the Mac App Store, Steam, or whatever.
Yeah.
And that goes also to another big thing that we're trying to solve in the Python ecosystem, which is the packaging story, right?
Yeah.
Which there are many solutions for, but just not one decided on, let's make this the standard, like, as easy as possible thing.
Yeah. It's getting better. Things are definitely getting better, but it's still, there is no Python build -- format equals exe,
Right.
where what comes out and then some sort of tooling that automatically signs that stuff with your certificate you've got as a Windows developer, so it doesn't get flagged as malware. And all like, there's just, even if you get the thing to build, there's like these 3 or 4 other steps. I'm thinking about in iOS, it's like, okay, we got it to run Python, but really what we needed to do is like integrate with Swift UI and have storyboards where I can weave it. And you're like, well, that's a long ways away. Like I know, but you got to go through those stages to get it. I don't know. It's just, there's a little bit further to go, I guess, but I would love to see it. And I think it'll happen probably.
It's not that you can't do it, it's just there's too much friction right now.
Yeah.
Yeah.
Yeah. Well, hopefully giving some people some ideas. Somebody's going to go start the Unity, the Pi Unity company or whatever, and let's make it happen.
Yeah.
Yeah. Oh, and also just real time follow up out there. Godot is apparently the pronunciation. It's French.
Sorry. Okay.
No, I didn't know it either. I think honestly, just shout out to everyone. If you have a weird name for your project on GitHub, put an MP3 and say this is how you say it. Just get it. Let's help us out.
Not that French is weird, but just we should actually do that with English projects too, right?
Yeah, absolutely.
To
I'm
make
thinking
it
even
accessible to the
as simple. Yeah, it has nothing to do with French. I'm thinking even as something simple as G unicorn is often said Gunicorn, and half the people out there are probably thinking, Michael, you're wrong. It's Gunicorn, not Gunicorn. But their logo is a green unicorn.
Yeah.
I'm like, well, it's probably the G stand, just G, and then certainly the unicorn part is probably unicorn because unicorn is, you know what I mean? But like, it's totally reasonable to look at it and go, Gunicorn, you know what I mean? But if they just put a little MP3, like or even just a word, it's pronounced GEE - unicorn. You know what I mean?
Yeah.
So
No,
I think we all need to do that. Yeah.
Yeah.
All right. Well, the chat is getting lively, but we're going to have to call it because we might be just a tiny bit over time, and it's getting late in your part of the world. So
Well, Thank you so much for having me on again, Michael. It was really a pleasure. Congratulations again on Talk Python in production.
Thank you, and computer
If
science from scratch as well.
Yeah, and
100%.
if folks want to check out the book, there's a website that I'm sure you'll put in the show notes, computersciencefromscratch.com, and you can just learn more about the different projects we do and some of the ideas in the book.
Yeah, awesome. People want to get in touch with you otherwise, how do they do that?
Sure. You can find me on X, I guess, at Dave Kopec, DAVEKOPC. And if you go to my website, davekopec.com, there's email and a bunch of other ways to contact me. So davekopec.com.
Yeah, I'll put it in the show notes for
Thanks,
people.
Michael.
Yeah, you bet. You bet. So, David, thanks for being back on the show. It's been really fun. And yeah, we'll talk to you later.
Awesome. Thanks, Michael.
Yeah, see ya.